Hello ninth graders, and welcome back. Today, we are going to be learning about the distance formula and the Pythagorean theorem. So what you're going to need, as always, a pen, a pencil, something to write on, so either some paper or a notebook, and put your thinking caps on, and let's get started. So what do you notice about these triangles here? There's something similar about all of them. What do you notice about them? Take a second, pause the video, and give it a try. What you should notice about all of these triangles is that they are all right triangles, if you remember some of the nomenclature for triangles from your geometry class. So they're all right triangles, and what this person, Pythagoras, discovered back in ancient Greece is he discovered that all right triangles share a similar relationship between the long side, or the hypotenuse, and the smaller adjacent sides. So what he found was that the square, right? Remember, the square is a quantity multiplied by itself. The square of the hypotenuse is equal to the square of one adjacent side in addition to the square of the other adjacent side. And that is true for all right triangles. And this is called the Pythagorean theorem. All right, so now what we're going to do is we are going to empirically prove the Pythagorean theorem using a measuring tape. Let's start off and try to find what the distance between the corner of the board and somewhere in the middle of the board is. So if we start off measuring the x-axis, we'll find that the width of the board is about 16 inches. So 16 inches. If we then measure the height at that point, the height at that point is right about 8 inches. A little bit shy, but just about 8 inches. And now, if we use our Pythagorean theorem, then what it should come out to is 16 squared plus 8 squared, giving us 320. But then we need to take the square root of 320, which comes out to 17.89 inches. And if we try it out, here we go. Measure tape at the corner. And this is right to, you see I've done this a little bit early, but there's a small point here that I drew earlier. Here we go, I got 17 point, it looks like a little bit shy 18, so about 17.8. All right, so let's try one more example. Okay. This time we are going to have our distance along the horizontal axis much shorter than the y. So let's measure right to this point here. And so as you can see here, the horizontal axis we're measuring out to 4 inches. So let me just draw a dot there at 4 inches. Then again, we're going to go completely vertical. From this point, we measure straight up. We're given 7.25 inches. 7.25 inches. And then if we put that into our Pythagorean theorem, it'll be 4 squared plus 7.25 inches. All right, so we know 4 squared is 16, right? And then if we add that to 7.25 squared, 7.25 squared is 52.56. So we add that to 16, we get 68.56. We take the square root of that, and we should get about 8.28 or 8.3. So let's see. We go to our corner here, and we're measuring right down to this point, and yes, that comes out about right. It's just shy of this first big mark after 8 inches. So right about 8.25, a little bit shy. So there we go. There are two examples proving empirically the Pythagorean theorem.
So, how does the Pythagorean theorem relate to the distance formula? Well, let's say I have a map where everything has a point on the x-axis and the y-axis. What could I specifically use the Pythagorean theorem to do? Pause the video for a second and think about it. I could use the Pythagorean theorem to find the distance between any two points, between really any two locations here. So how can we rewrite the Pythagorean theorem as the distance formula? I want you to use x and y for the adjacent sides, and I want you to use d instead of c for the hypotenuse. So again, pause the video here and give this a try. So how can we rewrite the Pythagorean theorem? Well, we start off with our Pythagorean theorem, c squared is equal to a squared plus b squared. Remember, we're replacing c with d, and so that becomes d squared. And then our adjacent side is really the distance between 2 points. So we would do x2 minus x1, and then b becomes y2 minus y1, so 2 y points. And then we will take the square root of both sides to get d alone, because we're looking for the distance. And so our equation becomes rewritten as d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared.
Listen, Tranquility Base here.
Mission Control to Space 320. Do you read me? Over.
I read you loud and clear, Mission Control. Over.
Thank you, Space 320. Glad to see you have arrived safely at the moon. Over.
Yeah, it only took 2 weeks. That's why I wasn't in a math video last week. Things are rocky here on the moon, but I'm here safe and sound, ready for my first mission. Over.
Thank you, Space 320. Your first mission. We need you to find the distance between the following stars and the sun. This is necessary for determining how long it would take for us to fly a satellite to those places. Over.
Got it. Just give me the list and I will get on it. Over and out. Let's see what NASA has sent for me to work on. Okay, I see a chart here. I have to find the distance in light years that each of these 3 stars are from the sun: Sirius, Polaris, and Alpha Centauri. To help me, NASA has given me the x, y, and z coordinates that each of those stars exist in. I've seen x and I've seen y, but I haven't seen the z coordinate too often. Maybe you can help me here. Pause the video and write down, what do you think it means to have 3 coordinates? Start the video again when you're ready. Did you figure it out? I think this picture will help. X, y, and z exist in 3 dimensions: length, width, and height. Now if you notice, the sun is at 0, 0, 0 for x, y, and z coordinates. That's because the sun is in the center of this system, and we are measuring how far all the other stars are away from the sun. So those stars are going to have coordinates larger than 0, somewhere out there away from the origin. Okay? Now the next step here is we need to calculate the distance. Well, we know the distance formula. Can we do it in 3 dimensions? Yes, we can. Here's what the distance formula looks like with 3 dimensions using x, y, and z coordinates. All right, can you help me out here? If I give you these coordinates, can you find the distance in light years that these stars are from the sun? Now, if we're going to do the sun, well, that's 0, 0, 0. The answer is going to be 0. That's because the sun is at the center. There is no distance to measure. The sun is right next to itself. Okay? Looking at Sirius, Polaris, and Alpha Centauri, and using that distance formula, pause the video and calculate the answer for how far they are away from the sun. Did you finish? Okay, let's take a look at the answer. From Sirius to the sun is 8.68 light years. From Polaris to the sun is 390 light years. And from Alpha Centauri to the sun is 4.3.
Space 320, this is Mission Control. We have received your charts and they appear accurate. Your country is thankful for the work that you have done. Now, we have one more mission for you before you return to Earth. Over. You are going to build a 50-meter high radio antenna on the moon. You are then going to calculate the distance between the radio antenna and a position that is within the line of sight on the moon. The reason why we're calculating the distance between the radio antenna and a line of sight on the moon is because radio waves cannot pass through big objects, so it cannot pass through the moon. Do you think you can calculate this given the parameters, Space 320? Over.
Got it. We'll calculate how far the radio signal will travel, over and out. The radio signal will travel a given distance based on the radius of the moon and the height of the tower. The radius of the moon is 1,737.5 kilometers. If the height of the tower is 50 meters, how far will the radio signal travel? Pause the video and see if you can figure it out. I will give you a hint. Use the Pythagorean Theorem. Can you see why? Are you ready? Our x distance can be represented as 1,737.5 kilometers, but we need to convert it to meters to have the x and y units align. So the x distance becomes 1,737,500 meters. Now, we need to put our variables into the distance formula. In this case, it is quicker to solve if we apply our variables to the Pythagorean formula. So here, d squared represents one of the smaller sides. The radius, r, of the moon represents a smaller side, and the radius plus the height of the tower is the hypotenuse. See, those are together to make one line, r plus h. This can be written as d squared plus r squared equals r plus h squared. We know the values for h and the radius, but we need to solve for d, meaning we need to isolate d. So we subtract r squared from both sides, and we get d squared equals r plus h squared minus r squared. Finally, take the square root of both sides. D equals the square root of r plus h squared minus r squared. Now, can you plug in the values and find the answer? Pause the video and try it on your own, and start again when you have arrived at an answer. Did you solve it? If we plug in our values, d equals the square root of 1,737,500 plus 50 squared minus 1,737,500 squared. D equals 13.181 meters or 13.18 kilometers. So, in conclusion, that means that as long as you are standing in the range of about 13 kilometers away from the top of that 50-meter tower on the moon, we will be in radio contact. But once you stand farther away, the radio is not going to work any longer.
Thanks for tuning in, ninth graders. We reviewed the Pythagorean Theorem and its rearranged form as the distance formula. We learned how to use it not only in 2 dimensions, but in 3 dimensions. This is a competency in order for you to move on to the next math level. So make sure you have mastered it to the best of your ability. There will be a quiz on the Google Classroom, so check that out once you are done with this video here. Thanks for tuning in again, and we'll see you next time.